Hello students, today we are diving into a very important concept, the methods of preparing carboxylic acids. Now think about this, the sour taste of vinegar, the sting of an ant bite, and even the preservatives used in foods, all of these connect back to carboxylic acids. But where do these compounds come from in the lab? The most common pathway is oxidation. Whether we start with alcohols, aldehydes, or alkylbenzenes, the key theme is that strong oxidizing agents push the molecule to form the COOH group. Substances like potassium permanganate, written as KMNO4, and potassium dichromate, written as K2Cr2O7, serve as powerful oxidants. Depending on the conditions, acidic, neutral, or alkaline, they can oxidize different organic groups. In short, oxidation is our main gateway to preparing carboxylic acids. Let's begin with primary alcohols. When a primary alcohol is oxidized, it passes through an aldehyde stage and then directly forms a carboxylic acid. For example, take a general alcohol, CH2OH. Under alkaline permanganate followed by water, this converts to our COOH. If we use Jones reagent, which is chromium trioxide in sulfuric acid, the transformation is the same. A specific example is 1-decanol with the formula CH3CH28 times CH2OH, oxidizing this with CrO3 in the presence of H2SO4 yields decanoic acid, CH3CH28 times COOH. Notice how the OH group at the end becomes a COOH group after oxidation. The take-home message: primary alcohols don't stop at aldehydes, they go all the way to acids. Now let's look at aldehydes. These are one step away from carboxylic acids, so only mild oxidation is required. For example, our CHO can be gently oxidized to our COOH. Reagents such as acidic KMNO4 or dichromate do the job effectively. You may also recall from earlier discussions that aldehydes can even be oxidized by mild reagents like Toluene solution. The logic is simple. Since the carbonyl carbon of the aldehyde already has a double bond with oxygen, it only needs one more oxygen to reach the carboxyl state. That's why aldehydes readily give carboxylic acids, even under mild conditions. Aromatic carboxylic acids are another fascinating case. Here we start with alkylbenzenes, benzene rings with alkyl side chains. Vigorous oxidation with chromic acid or permanganate converts the entire side chain into a single COOH group, no matter how long the side chain originally was. For instance, toluene, which is C6H5CH3, oxidizes completely to benzoic acid C6H5COOH. The benzyl carbon must have at least one hydrogen atom for this oxidation to happen, which is why tertiary side chains remain unaffected. This property is so powerful that it simplifies aromatic chemistry. No matter how complex the alkyl group, strong oxidation chops it down to COOH. Let's walk through a stepwise example, the oxidation of toluene. Toluene, C6H5CH3, first oxidizes to benzyl alcohol, C6H5CH2OH. This then oxidizes further to benzaldehyde, C6H5CHO. Finally, the aldehyde is oxidized to benzoic acid, C6H5COOH. All of this happens under strong oxidizing conditions such as alkaline potassium permanganate. During the reaction, you will also notice the brown precipitate of manganese dioxide being formed, which is a clear visual cue. So, what begins as a simple alkylbenzene ends up as an aromatic acid, a transformation widely used in industrial production of benzoic acid. So, to wrap up, the preparation of carboxylic acids revolves around oxidation. Primary alcohols get oxidized to acids Aldehydes need only mild oxidation, and alkylbenzenes give aromatic acids when treated vigorously. Regardless of the starting material, the product is the same functional group, the versatile COOH. I hope this session showed you how simple yet powerful these pathways are and how everyday compounds like vinegar or benzoic acid in food preservation connect back to these reactions. Chemistry really is the invisible bridge between the lab and our daily lives. See you in the next class with more fascinating concepts and their real-world relevance.